Electronics Pariksha channel. Today we'll discuss the problems of diode circuits from analog electronics. Let's see the question. Determine the current I for the network shown below. If you observe the diagram, we have got the two silicon diodes, diode D1 and D2. In a PN junction diode, the P type, when the P type is connected to higher potential and the N type is connected to lower potential, the diode is said to be forward biased. And diode starts conducting, acts as a closed switch. Similarly, for the diode, when the P type is connected to lower potential and N type is connected to higher potential, diode is said to be reverse biased. Diode does not conduct and acts as an open switch. So based on this concept, if you observe carefully, here the diode D1 is forward biased, acts as a closed switch. Diode D2 is reverse biased, acts as an open switch. So the current flows through the resistance and through the diode D1. So by applying KVL in this loop, we have got E1 minus I into R minus VD1, that is the diode cutting voltage, minus E2 is equals to 0. So by substituting these values, we get E1 is 20 volts minus current is unknown parameter here. What is the resistance? 2.2 kilo ohms into 10 to the power, means 10 to the power of 3, minus diode cut-in voltage is 0.7 volts minus E2 is 4 volts is equals to 0. So the current I is given as 20 minus 0.7 minus 4 divided by 2.2 into 10 to the power of 3, which is equals to 6.95 milliamps. So the answer is option B. For the silicon diode, you have to remember, for silicon diode, the cut-in voltage is 0.7 volt. Whereas for the germanium diodes, it is 0.3 volts. This is important. Okay. Now let's see one more question. What are the output voltages for the given circuit? Assume it is silicon diode. So this is very important. Here he is telling the diode is silicon diode. So what is the assumption when it is silicon diode? The cutting voltage is 0.7 volt. Okay. So now see, you see the input signal is a triangular waveform. The positive peak voltage is plus 16 volt. The negative peak voltage is minus 16 volt. So we will analyze this in two cases. In case 1, we will consider the positive half cycle. Let's read out the circuit, the resistance, diode, and the reference voltage, that is 4 volts. Okay, this is the output voltage. In the positive half cycle, what is the maximum voltage that is available? That is plus 16 volt. So in this case, the diode D acts like a reverse biased diode. It acts like a reverse bias. So open switch. Diode acts like a open switch, no current flows. Hence, the output voltage is equals to plus 16 volt. Whereas in case 2, we have to consider the negative half cycle of the input voltage. In the negative half cycle of the input voltage, the maximum negative voltage is minus 16 volt. Here also we have the resistance, diode, and the reference voltage is 4 volt. In this case, if you observe carefully, the diode is forward biased. Diode is forward biased. Hence, the diode starts conducting. So, diode is forward biased. Forward biased. So, it acts like a closed switch. It starts conducting. So, here in this case, the output voltage V out is equals to 4 minus diode cut-in voltage. So in this case, the output voltage V naught is equals to 4 minus 0.7, which is equals to 3.3 volts. So here, the minimum voltage is 3.3 volts. So the option answer is option B. So we'll see the next question. For the given clamper circuit, find the output voltages between T1 and T2 instances. Assume the input as shown in figure 2 and diode is the silicon diode. Again the diode is the silicon diode. So the cut-in voltage assumption is zero point 0.7 volts. And if you observe the question carefully, he's asking us to find out the output voltage between the instances T1 and T2 only. So, between the instances T1 and T2, what is the input voltage? Input voltage is minus 10 volt. So, let's read out the circuit with that. Input voltage is minus 10 volt. There is a capacitor C and diode. Reference voltage is 2 volts. So, this is the circuit for which we need to find out the output voltage. So in this case, if you observe the diode is the forward biased. Diode is forward biased and current flows in the circuit in this direction. When the current is flowing in this direction, the capacitor charges to the value Vc. So by applying Kirchhoff voltage law, by KVL, we get 2 volts minus Vd1 diode cutting voltage minus Vc plus 10 is equals to 0. So here the capacitor voltage Vc will be 2 minus zero point 0.7 plus 10, which is equals to 11.3 volts. This is the capacitor voltage. So when we get the capacitor voltage, it is easy to find the output voltage. To find out output voltage, we need to apply the Kirchhoff voltage law in this loop. So the output voltage by KVL again, output voltage is equals to Vc minus 10, that is 11.3 minus 10 volt, which is equals to 1.3 volts. So the output voltage between the instances T1 and T2 is equals to 1.3 volts. So the answer is option D. Coming to the next question. For the circuit in the above figure, the Zener current Iz and the power dissipation R. So he is asking us to find out the Zener current Iz and the power dissipation of the Zener diode. So here Iz is equals to E minus Vz divided by R. E is the voltage 20 volts input voltage, that is Zener voltage is 7.5 volts divided by the resistance 620, which is equals to 20.16 milliamps. Whereas the power dissipation Pz is equals to Vz Zener voltage multiplied by Zener current. Zener voltage is 7.5. Zener current is 20.16 milliamps, that is 10 to the power minus 3, which is equals to 151.2 milliwatts. So the answer is option A, 20.16 and 151 milliwatts. Let's see one more question. Which of the following is the main application of Zener diode? Zener diodes are basically heavily doped diodes. Zener diodes are basically heavily doped diodes. So due to this heavily doping nature, they have got very thin depletion region. Thin depletion region. Whenever a diode has a thin depletion region, it has got a lower breakdown voltage. Lower breakdown voltage. Here in this case, it is Vz. So whenever the reverse bias voltage applied across the Zener diode reaches this breakdown voltage, it starts conducting heavily. It starts conducting very heavily, keeping the voltage across it constant. So this constant voltage nature makes it usable for the voltage regulation purpose. So it is used as a voltage regulator. This is the major application of Zener diode. So the answer is option A. Next question. Using a DC and AC voltmeter to measure the output signal from a filter circuit, we have obtain readings of 25 volts DC and 1.5 volts RMS. So what is the ripple factor? Ripple factor is equals to VRMS divided by VDC into VRMS is 1.5 volts, VDC is 25 volts into 100, which is equals to 6%. So the answer is option B. So the next question is, in a center tap full wave rectifier, Vm is the peak voltage between the center tap and one of the secondary. The maximum voltage across the reverse bias diode is. So basically he is asking for peak inverse voltage. He's asking for peak inverse voltage of the diode in center tap, which is 2 times of Vm. So how does it work? We'll see. This is a center tap full wave rectifier diagram, secondary upper wing and secondary lower wing. We have got two diodes in the center tap rectifier, diode D1 and D2 and load resistance RL. This is diode D1, D2 and load resistance RL. So during the positive half cycle, here in the upper primary winding it is Vm, in the lower primary winding also it's Vm. So the diode D1 acts as a forward biased closed switch and D2 acts as a reverse biased open switch. So when the diode D1 acts as a closed switch, diode D1 acts as a closed switch and diode D2 acts as an open switch during the positive half cycle. So the current flows in the upper primary winding loop and the voltage drop across the load resistance will be plus Vm. Now, in this case, the voltage across the D2 by applying Kirchhoff voltage law, you can find out the voltage across VD2 is equals to VL load voltage, that is a load voltage across the load resistance plus voltage across the lower primary winding, that is VM. So VD2 is equals to VM plus VM, which is equals to 2 VM, means 2 times of the maximum voltage. So the answer is option B. Next question, the efficiency of the half wave bridge rectifier under the best condition is. So the rectification efficiency is given as output DC power, output DC power divided by input AC power into 100, which is equals to the output DC power is nothing but I square DC into RL divided by input power is I square RMS into small rf plus capital RF into 100. Here the small rf is nothing but the diode forward resistance. Diodes forward resistance. So now for the half wave rectifier, we have the IDC is equals to Im by pi and IRMS is equals to Im by 2. Substituting these values, we get Im by pi whole square into RL divided by Im by 2 whole square multiplied by small rf plus capital RL into 100, which can be equal to 40.6 divided by 1 plus small rf divided by capital RL into 100. In case of half bridge rectifier, the resistance, diode forward resistance is far lesser than load resistance. So this can be approximated to 40.6 percentage. So the answer is option C. In case of full wave rectifier, for full wave rectifiers, the rectification efficiency is 81.2%. This is also very important in the examination point of view. Now, look at the next question. The ripple frequency of the full wave rectifier is. The ripple frequency of the full wave rectifier is. If you observe carefully the diagram, this is the input voltage for the full wave rectifier. That is a sinusoidal wave, having the frequency Fi, whereas the output voltage wave will be the positive half cycle remains as the positive half cycle, and negative half cycle also is converted to positive half cycle. So if you observe carefully, the output frequency is equals to 2 times of input frequency. So it is double the input frequency for the full wave rectifier. Next question. The Schottky diode drops about 0.3 volts when conducting. The diode is connected in series with the resistor of 1 kilo ohms and forward biased with the voltage of 1 volt. Calculate the diode current. Let's draw the circuit. So the voltage applied is 1 volt and the resistance is 1 kilo ohm. So the current flows in this direction I. I is equals to 1 minus 0.3. 0.3 is the cutting voltage of Schottky diode divided by 1 kilo ohm. That is 1 into 10 to the power of 3. So the current here is 0.7 milliamps. So the answer is option B. Now let's look at the next question. In the full wave rectifier with a center tap transformer, if the voltage between one end of the secondary winding and center tap is 300 volts, what is the peak inverse voltage? We have already seen. Peak inverse voltage for the center tap transformer is 2 times of Vmax. That is 2 times of 300 volts, which is equal to 600 volts. Answer is option C. Next question. The ripple factor in case of full wave rectifier is. So the ripple factor can be given as under root I square RMS divided by I square DC minus 1. For the full wave rectifier, IRMS is equals to Im by root 2, whereas IDC is equals to 2 Im by pi. Substituting these values, gamma is equals to I square RMS means Im by root 2 whole square divided by 2 Im by pi whole square minus 1, which is equals to. So by substituting these values, you will get an answer as 0.48. So the answer is option C. Now look at the next question, that is form factor of the half wave rectifier is. So the form factor is given as Vrms divided by Vdc. For the half wave rectifier, Vrms is Vm by 2 and Vdc is Vm by pi. By substituting these values, Vm by 2 and Vm by pi, you will get answer as 1.57. So the answer is option D. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.